Okay, hi class. So I just wanted to go over some problems, make a little video going over some problems in the forces unit. So just to give you, to highlight some of the things that you need to know and that are important for solving these problems. Um, okay, so and I figure the easiest way to do that is just to go through solving some problems and we can explain the concepts as we're going through it. All right, so first of all, let's do this one. Analyze the free body diagram. So they tell us that we're being given that there's a net force of 600 newtons acting on this object, and the speed of the person is decreasing. So a net force means when you add up all the forces on the object and forces that are in opposite directions, we'll subtract uh, what is the sum of all those forces. So the net force is the sum of all the forces. So in this case, we have a downward force of 700 newtons that's due to their weight or the force of gravity. And we have an upward force of drag, uh, which is the force of air against the person. And we know that the speed is decreasing. So if the speed is decreasing, clearly the person is falling downward. And if the speed is decreasing, the force that is causing that speed to decrease must be going in the opposite direction. So we know our net force is upward. Our acceleration is upward. Okay, so we have an upward net force. That means the force in the upward direction is larger than the force in the downward direction, or the individual forces. The forces in the upward direction must be larger than the forces in the downward direction. So if we have a net of 600, that means the upward forces must be 600 larger than our downward forces. And since these are our only forces involved here, we simply say 700 plus 600 is 1300, and that's how we get our upward force. Okay, so just basic ideas. If I've got a force of 10 newtons in one direction and I've got a force of 3 newtons in the opposite direction, then our net force, F net, is going to be 7 newtons in this direction. So forces in the same direction add, forces in opposite directions subtract. And the net force is the sum of all the forces. All right, let's do another one. Okay, here it says the only thing that we're given is constant speed. And so what you need to know here is that if we are traveling at a constant speed, they just told us that the sum of the forces on the object must be 0. So constant speed tells us that the sum of the forces acting on the object is 0. If the sum of the forces acting on the object is 0, then we must be traveling at a constant speed, which could include a constant speed of 0, which would be at rest. So if an object is at rest or moving at a constant velocity, the sum of the forces must be 0. If the sum of the forces are 0, the object is either traveling at a constant velocity or has a constant velocity of 0, meaning at rest. If the sum of the forces is not 0, the object must be accelerating. If the object is accelerating, the sum of the forces must not be 0. Okay, but so since we know the speed is constant, we immediately know that the sum of the forces on the object must be 0. So therefore, the net force on the object must be 0, which means the upward and downward forces must be equal and opposite. So we have a downward force due to weight of 700, therefore our upward force must be 700 newtons as well. Okay, analyze this free body diagram. Well, here the bicyclist is on a flat surface. In the upward-downward direction, you want to look at the upward-downward direction independently of the horizontal direction. So the vertical direction we're going to look at independently of the horizontal direction. So vertically, clearly this person is not going up at all. They're not going up a hill. They're not floating into the air. They're not going down. They're not going through the ground. So they don't have any velocity in the up-down direction. And so the forces in the up-down direction must be balanced. So if we have 800 newtons down, we must have 800 newtons up. The force of gravity down, the force of the surface, the normal force back up are equal and opposite. In the horizontal direction, it says that we have a net force of 50 and we are slowing. So clearly we're traveling to the right. If we are slowing, our net force must be to the left, meaning this leftward force must be larger than the rightward force. So we have to put a number in here, less than 70. And our net force is 50, so this must be 50 less than 70, which is where we come up with a 20. Okay, so our net force is, we have 70 in this direction and 20 in this direction. So our net force is 50 in this direction. Okay, so we have a net force of 50. So these two forces must net out to be 50. And if we are slowing, the force is working against us. So the net force must be acting in the opposite direction of our motion. Okay, next one. Okay, so here the first question is how many forces are acting on the bicyclist? And the bicyclist is pedaling to the right. So we clearly have an applied force acting to the right. There's always going to be a force of gravity or weight downward. They're on a surface, so there's definitely a normal force acting back up again. And if we read the problem further, it'll talk about a drag force. So we have 4 forces acting on the object. So we put 4 in. And it's asking for the net force. So let's read our problem. Okay, an 80-kilogram bicyclist, they just gave us the mass of the bicyclist, not the weight, the mass. The mass is a measure of how much material they have in them. Is pedaling to the right, causing her speed to increase at that rate. That's an acceleration, 4.2 meters per second squared. Despite experiencing a drag force of 50, so we know this opposing force is 50 newtons. And despite the drag force, she is nevertheless accelerating to the right. So she is pedaling to the right, causing her speed to increase. Okay, so she is increasing to the right. Neglect any friction impeding her motion. What is the net force? Well, we know from Newton's law, F net equals ma. The net force is what causes the acceleration, not the individual forces, the sum, whatever the sum of all the forces is, whatever the net force, that is what causes the acceleration. So our acceleration is F net over m. Okay, so our net force is what we're trying to find. So actually, let's not write it this way. Sorry, let's just leave it in this form. The net force is what we're trying to find. Our mass of the bicyclist is 80 kilograms, and our acceleration is given to us as 4.2 meters per second squared. So 80 times 4.2, put that into our calculator, and we get 336 newtons. Okay, so just pretty simple calculation here. F net equals ma. Okay, so they gave us the mass, they gave us the acceleration, so it was pretty simple to calculate the net force of 336 newtons. Okay, so we know that our net force is 336 newtons. This is F net. And this is comprised of 2 forces. This is, we're pedaling at some force, and we're having an opposing force of 50 newtons. So what minus 50 is going to get us to be 336? This is our applied force, our pedaling force, okay? So how much force is the bicyclist generating through her pedaling? Well, the only way for whatever this is, minus 50 has to equal this. So therefore, this is 386, right? FA minus 50, it's got to equal 336. We add 50 to both sides. And you get our applied force is 386 if you like to do it with a formula. Okay, so we get 386 newtons, and we're good. All right, next problem. Okay, what do we have? We have a 60-kilogram bicyclist. They just told us the mass, 60 kilograms. Initially at rest, so they give us an initial velocity of 0. Pedals to the right, generating 190 newtons of force. So that's our force applied is 190 newtons. Okay, for 4.9 seconds. They just gave us a time. During this time, she experiences a 60 Newton drag force. So you're We have an opposing force of drag of 60 newtons. Neglect any friction. Okay, what is the magnitude of the net force? Well, the net force is 190 minus 60. Okay, so that's not so bad. 90 minus 60 is 30. 130 newtons of net force in the rightward direction. F net equals 130. Okay, what is her acceleration? Well, we can use F net equals ma, right? F net forces are what cause acceleration, ma. So a is F net over m. Our net force is 130 newtons. Our mass is 60 kilograms. So we get 2 and 10/60th, which when we put it in our calculator is 2.16 meters per second squared. 2.167, really. 7 meters per second squared. Okay, and so we've calculated our acceleration. We're done with this. We finish this, and we finish this. All right. Now we want to know her final speed. Well, now we know acceleration. We just calculated acceleration, so that's something that we can add to our known quantities over here. Okay, so our acceleration is 2.167 meters per second squared. So we want to know a couple things. Her final speed and how far does she travel? Well, final speed's pretty simple, right? We want to know final speed is whatever speed you started at plus your acceleration times time. Well, we started from rest, so our initially at rest, right? Remember that? Initially at rest. That's where we got this VI equals 0 from. Acceleration we just calculated, 2.167, 2.17, let's use that, 2.17 times time, 4.9 seconds. Okay, so 2.17 times 4.9. We multiply that and we get 10.6 meters per second. Our final speed after those 4.9 seconds, or right at the 4.9 second time, is 10.6 meters per second. So we plug that in here. Our final speed after 4.9 seconds is 10.6 meters per second. All right, well, how far does she travel during that time? A couple of ways you can do that. You could do distance equals velocity initial times time plus 1/2 at squared. Or now that we know the initial velocity is 0, we now know our final velocity is 10.6. So we can calculate pretty easily our average velocity, which is right smack in the middle of these two, which is 5.3 meters per second. And we know distance equals average velocity times time. So 5.3 meters per second times 4.9 seconds equals 26 meters. So we plug that in over here, and we are done. All right, hopefully that is good. Let's do one more. Okay, here we have a teacher in a parachute. All right, how many forces are acting on the system? Well, we have a force downward, that is the force of gravity. And we've got a force upward, which is the force of drag, okay, which is 1,500 newtons. Okay, a 70 kilogram teacher, that gives the mass of the teacher. The mass is 70 kilograms. A 70 kilogram teacher is skydiving, including the parachute. So that's the teacher and the parachute together are 70 kilograms of mass. The system experiences 1,500 newtons of drag force. How many forces are acting on the system? Well, gravity down, drag up, that's 2 forces. What is the magnitude of the net force? Okay, well, we don't have an acceleration, so we can't compute it by using F net equals ma. So the way to figure out the net force is we have to figure out what this gravitational force is. Now, what is the force of gravity? So this is an important relationship. The force of gravity on an object on Earth is the mass of the object times the acceleration due to gravity. Okay, I'm going to write that as little g, the acceleration due to gravity. Okay, so this is, you could think of little g, lowercase g is the acceleration due to gravity. Okay, and I'm going to write it as just a lowercase g instead of a sub g. I'm going to write it as lowercase g because that's how it is on the reference table. So the formula on the reference table is weight is equal to weight, which is really the force of gravity on an object, is equal to the mass of the object times the acceleration due to gravity. Okay, which on Earth is 9.8. So our weight on Earth, or the force of gravity that an object has on Earth, is the mass of the object, which in this case is 70 kilograms. Okay, let's say 70 kilogram teacher and parachute. So 70 kilograms of mass times 9.8 or 9.81, whatever you like, meters per second squared. Okay. So if we plug that into a calculator, we get 687. So I just paused and used the calculator. Okay. So that comes out to be 687. So this is, this is 687 newtons of downward gravitational force. So now we can figure out the net force pretty simply. We just take our bigger force minus our smaller force, and we get 813. Okay, so our net force is 813 newtons in the upward direction. Okay? So what is the magnitude of our net force? 813 newtons. And having a force bigger in the upward direction, what that means is the parachute has just recently opened up their parachute, and there's so much force because they were going fast through the air. When they first opened that parachute up, there's a lot of force on the parachute, which is causing them to not move in the upward direction, but at least accelerate in the upward direction. Their speed is changing in the upward direction. Okay, their force is in the upward direction. Their acceleration is always in the same direction as their force. Okay, so if you have a net force in the upward direction, your acceleration is in the upward direction. So it's causing, an upward acceleration is causing the downward speed to decrease. So he is in the process of slowing down. And eventually he'll hit kind of a steady state, and he'll float down to the Earth at a constant speed and hit the Earth with a speed that is comfortable. Okay, so we know his force is 813. Now we're trying to find this acceleration. What is its acceleration? Well, what is our formula? F net equals ma. Okay, so A equals F net over m. Well, our net force we just figured out is 813. The mass is 70 kilograms. And so we divide those and we get our acceleration, 11.6 meters per second squared in the upward direction. Okay? So we just plug that in. So each second, his downward speed decreases by 11.6 meters per second. So he's going very, very fast because he was falling through the air without a parachute. Now that his parachute is open, his speed is decreasing by 11.6 meters per second each second. So his speed is rapidly decreasing. It means he's got an upward acceleration, and that will last for maybe 1 or 2 seconds, and then he will, after that point in time, he will float down to the ground. All right, so what's happening at this moment in time? His speed is decreasing. All right, we'll do one last one. All right, again, a 70 kilogram teacher. They give us the mass of the teacher, 70 kilograms. Is skydiving. As the parachute opens, the system experiences 1,500 newtons of drag. So a similar place. Is the exact same problem? This is the exact same problem. Sorry. All right, let's move to this problem. This will be our last problem. Okay, a 1.6 kilogram fan cart. Okay, so they just gave us the mass. Mass is 1.6 kilograms. It's moving to the right. It's got 0.3 0.39 newtons of force. So we've got a force to the right of 0.39 newtons. Neglect friction, neglect drag, how many forces are acting on the cart? So we always are going to have this gravitational force, as long as we're on Earth, and we're going to have an upward normal force in this case because we're resting on the surface. So our total number of forces is 3. All right, what is the magnitude of the normal force? Well, the normal force is equal and opposite to the force of gravity. Well, what is the force of gravity? The force of gravity is mass times the acceleration of gravity. Okay, so our mass is 1.6 and the acceleration of gravity is 9.81 meters per second squared. And that is going to equal, when we put it into a calculator, 15.7 newtons. Okay, so we come over here and we put 15.7 newtons. That is our force of gravity, which is also equal to our normal force. Okay, what is the net force on the fan cart? Well, the normal force and the gravitational force are equal and opposite. They cancel each other out. So the only force that remains is this thrust force of 0.39 newtons. So the net force is 0.39 newtons, which is to the right. Okay, and what is the magnitude of the cart's acceleration? Well, whenever you're being asked for acceleration, the first thing that should pop into your mind is F net equals ma. The net force causes acceleration. So our acceleration can be found if we know the net force and we know our mass. So in this case, we do know the net force, it's 0.39 newtons, and we do know the mass, it's 1.6 kilograms. So we plug that into our calculator, and I did earlier, so I know the answer is 2.44 meters per second squared. Okay, so we write that down, 0.244 meters per second squared, accelerating to the right. Okay, so if our force is to the right, means we're accelerating to the right, so our speed is changing to the right. And since we're already moving to the right to begin with, our speed is going to be increasing. Alrighty, so hopefully that helps. I think the important concepts are net forces cause acceleration, not individual forces. It's the sum of all the forces together, the net forces that cause acceleration. And the other key thing really is that weight of an object, force of gravity. The weight is the force of gravity on an object, and that can be found by taking the mass and multiplying it by the acceleration due to gravity, which on Earth is 9.81. So mass times the acceleration due to gravity will give you the force of gravity, and that's obviously very important in solving some of these quick equations. And then last but not least, forces. If the forces cancel in one direction, it's not going to affect the motion of the object, and only the net force in the in the perpendicular direction will be causing the object to accelerate, and it'll only be accelerating in that same direction. Alrighty, if there's any questions, send me some screenshots. I'll help you through the problems. Otherwise, try and finish this up. This unit up over the weekend, and then we'll take a test next week. Free fall, possibly a second test next week on the forces stuff, and then we'll begin projectile motion next week. Okay, thank you.